Hello, everybody. Today we are talking about many models forecasting, and together with Lara, we have Ryuta. Ryuta, hi.
Hi, I'm Maria. Hi, Lara.
Amazing. So, Ryuta, can you tell us a little bit more about what you built and why the many models forecasting solution was created?
Yeah, sure. So many model forecasting, we abbreviate it like MMF, is an open source framework for large scale forecasting that runs on Databricks. And so if you're working on a large scale forecasting, by large scale, we mean you have a lot of time series in your data set for which you need to produce forecasts for. Then you can use MMF to apply right now 40 plus different models onto each one of your time series. And you can evaluate and select the best model for each time series and get the forecast from those best performing models. So that's what MMF is in a nutshell. And the reason why we built it is, yeah, I mean, Maria and Lara, you're also specializing in machine learning, data science. And I think forecasting is probably the most widespread use cases, applications of advanced analytics. So I've been at Databricks for 2 years. I've spoken to a lot of customers, but I heard this topic forecasting from customers from all different verticals, for everywhere, from every department. So that's how important it is. And through this, like many conversations, we kept on hearing like two big requests. And one was a customer wanted to see how they can use Spark's distributed compute to scale, their forecasting solution, because they were, no longer dealing with tens or hundreds of time series, but they were dealing with hundreds of thousands of time series, and sometimes even millions of time series. And they wanted, Spark experts, so Databricks, to come to them and show them how they can scale their solution beyond hundreds of thousands. So that was one big request we kept on hearing. And the second request was, so these customers, they were aware of what was happening in the space of forecasting. So they were typically using traditional models, statistics basic model, like ARIMA and so on, but they knew that there were a lot of things happening in deep learning. And there were also newer models coming out from pre-trained transformers. And they wanted a way to evaluate these models against their benchmarks. They wanted to see how well these new models perform against the traditional, more established models. So we kept on hearing these requests, and that was 2 years ago. We got together a group of field engineers from Databricks, and we decided to work on this project called MMF. So that's where we got started.
Excellent, amazing story. And when you said these 40 plus models, what does this 40 plus mean? Is it the models we support, or what does this mean?
Yeah, so these are individual models that we support, that MMF support. And so yeah, when you look at like the market of forecasting models, there's hundreds of them, or like even more. And we looked at it, and then we classified these many models into 3 buckets. So one bucket is called local models, and this is when you train one model per each time series. So if you had 1,000 time series, you end up having 1,000 models. Models like ARIMA, ETS, Profit, these belong to local models.
And sorry, when you say 1,000 time series, you mean, for example, I'm tracking different features or for different like time series across different stores, or time series, like what is something like that?
Yes. Typically, a lot of customers want to produce forecasts for SKUs, how many SKUs will be sold next week, next month, and so on. Yeah, so that's forecasting time series item.
Amazing.
Yeah, so that was the first bucket, the local models. And the second class of model was, we call it global models. And these are models where you train a largish model for multiple time series. So imagine you have like 100 time series, you train one big model to produce forecasts for all those time series.
I see. So like if you have 300 stores, you throw them all in there and they let the model like learn across all the different stores.
Exactly, you're right.
Okay.
And typically you use machine learning based models or deep learning based models for this. And the third type of models that we've been seeing in the last half year or a bit longer is called foundation time series models. And these are typically transformer-based models, not necessarily. And they're pre-trained on millions or billions of time points. And they are supposed to work out of the box without fine-tuning or without training. So you just provide the history, they generate the forecast. So yeah, we looked at this, many different models from these perspectives, 3 buckets, and we decided to select the models that are widely adopted by our customer bases, popular models, ARIMA, ETS, and the models that we believe are bulletproof. They're good models. So this is an opinionated list of models, 41 different models, but it's still growing.
And why not using AutoML here? Like, what are the benefits?
Yeah, Databricks AutoML is a great tool. I use it all the time. And it's really good to get started with the project. So if you're right now about to get started with forecasting, then it's a great tool. You can click the button through, you can point to the training data set, and you can generate forecasts and also metrics. So you're going to have a good vibe check how difficult your problem is. And then it also gives you a generated notebook upon which you can develop more sophisticated solution. And MMF is something that is a few steps closer to production, I would say, because it gives you a lot of freedom, flexibility to configure your cross-validation, to select multiple models. So we do support 40 plus different models. You can narrow that down. And it also allows you to perform fine-grained model selection based on the cross-validation strategy you specified. So these are a few steps before the production where you're sure you have a list of models that you want to apply and you want to bring them into production.
And then is it best practice to say start with AutoML to see how difficult your problem is and if your time series actually is something you could work with? And then as you progress and learn more about your data and your problem, then move to the solution?
For now, yes.
Okay.
Yes. I know that there's a lot of things going on also in AutoML, and the solution is probably getting more and more closer to production as well. So yeah, you should keep your eyes on it. But at the moment, I think that's the approach I recommend.
Cool. Ryuta, should we go to the code?
Oh, yes. Let me share my screen with you. So yeah, as Maria just said, we have a public repository in GitHub for many model forecasting, MMF. So you can access all the code. And you can look up how things are implemented here.
Can we start then understanding a little bit how the repo is structured and what are the basic components you have to be aware of?
Yeah, so there is an extensive description on the README. It's going to describe what the model, what the project is about, and how to get started. And if you want to see all the supported models, you can. It's also written in the README. So here, for example, for local models, we have the support for all these models coming from different frameworks. Mm-hmm. These models come from Stat Forecast, some model come from RFable, and some model come from SK TimeBat. And if you scroll down, you can see how you can get started with the global models. And you can also see a list of models that we support from this class of model. We have integration with Neural Forecast, which is an open source library that supports a lot of global models, great ones. And this is a list of active models right now. And if you scroll even further down, we do have also support for foundation time series models. Chronos is coming from Amazon Research, and Moirai is coming from Salesforce. And we're actively working on integrating other models, more models into this list.
And then if someone is starting, do you recommend they go through all the models? Or like how would they... Okay, I understand the difference between local, global, and foundational models. Probably they would have an idea on that. But between the different models, are we saying in the first pass, just try them all?
Yeah, that's a good question. So just to bridge how you can get started with MMF is that, let me just zoom out a little. You can get this GitHub repo and clone it into your Databricks workspace. And that's exactly what I did here. So here you can see all the repos that I've cloned. And here we see many model forecasting. Nice. If you click on here, you're going to see the same structure as you saw in the GitHub. And inside here, we have a folder called examples. And if you click further here, we have a lot of notebooks that's going to walk you through how you can get started based on the scenario that you want to work on. So for example, right now we're looking at local univariate monthly notebook. And let me just zoom out again. So this notebook walks you through how you can apply MMF on using local models on a univariate time series with monthly resolution. And let me scroll down. It comes with like cluster setup configuration recommendations. It runs on a public data set. It does prepare the data set for you also on the notebook. So it should run end to end already. And if you scroll down a little bit, you can also specify the type of models that you want to apply to your time series. And here you're getting back to your question, Maria.
Amazing.
So which models to apply? It does require some knowledge about the model. So you need to know the pros and cons of each model. And this is something that you need to study or understand. I can just very quickly walk you through. These are the list of local models that we support. Some of them are naive models, so they just extrapolate what they saw in the back, nothing sophisticated, maybe just moving average and so on. These are typically used for benchmarking. We have statistics-based models like ARIMA, auto-regressive model, exponential smoothing. There's also a class of model called intermittent forecasting model, which is proven to perform well on an intermittent sparse time series. If you have a sparse demand time series, SKUs that are sold only once in a while, these models are proven to work well. And then there's also a bunch of other more sophisticated models like harmonic regression, T-bats, and so on.
Amazing. And because since you mentioned the cluster and the compute we need to run these examples, is there any, do you have some specific like type of VM GPUs needed for this?
Yeah, it's a good question. And that's also the reason why in the README, we have split the local model, global model, and the foundation model section, because each of these models require a different configurational setup for the cluster. So local models, they run faster on CPU. So you would want to launch a CPU, maybe with multiple workers.
Okay.
For global models, you might want to use GPU. You might even want to use multiple GPUs if you want to distribute the training. And
like
also the same for
node multi-GPU cluster. Yeah, okay.
Yeah, single node multi-GPU cluster. And for foundation models, since these are also based on transformer neural network architecture, you would want to also have GPU cluster attached to it.
Okay.
When you decide whether to use local models or global foundation, is it only based on costs, or do you have any recommendation on how to choose which one to use?
Yeah, so generally speaking, local models are typically good with explainability and transparency, because at the end of the day, you have a generalized linear regression model that is being applied for each time series, and you can look at the coefficient and reason about your forecast. So it provides you certain explainability, whereas global model work more like a black box, where you're training multiple time series at the same time. You don't know how each one of them correlate, but it's captured as weight in this big neural network. But it is in certain scenarios, it is proven to work better than local models. But my recommendation is that you try models from different paradigms. So local models, global models, and foundation models, because you actually don't know which model performed the best for each time series, especially if you have a heterogeneous mixture of time series. Sometimes the naive models outperform the latest foundation models. That's possible. So this is also the idea of MMF, so that you can apply all these 40 different models from different paradigms onto each one of your time series and let them compete with each other.
So we say don't just focus on the fancy models, go back to basics too.
Yeah, definitely.
Excellent. So let's go back to the data a little bit. I saw in the notebook you showed that you kind of handle the data prep before you start the modeling. So can you tell us a little bit what is the best way to do that? Because given maybe different models, you have to do different things. I'm just saying now.
Yeah, great question. So, so we're using a public data set for all these example notebooks. And this is how your input data set can look like. So we put it into a delta table. And in that table, in one column, we have the state column or timestamp column that, this is a monthly time series. So we do have a monthly timestamp. And in another column, we have, we call it unique ID in this specific table, but it can be something else. So this column basically groups your time series together. So in this table, we have multiple time series. So if you scroll down, we start seeing M2. This is a different time series, then M3 and M4 and M5.
Okay, and this this group IDs, we can think of this as the SKU of a product that we group in by, and then we have the time series for an SKU.
Yes, you're right, 100%. And then we have our target variable that we want to forecast. And you can also include exogenous regressors if you want to use the model that can use them to make forecasts. So things like future dynamic regressors, and you can add them as columns here.
Cool.
So we did unify the format of the input, so you can use the same input for all 40 plus different models.
That is excellent. So then it's the same across any of the other type, any model type you want to do, like local, global, foundational.
Yes, the input format is the same for all the different models. So some models can use exogenous regressors and some models can't.
Okay.
So the models that can't use them, they will just not take those exogenous regressors into account.
Like it's in the code to exclude them. They don't have to do anything. Like the customer doesn't have to do anything. Okay, amazing. Cool. And I saw that most of the exams were about univariate time series. So what is the case there? Is it only univariate? Can we support multiple features per time series?
Yes. So we have another notebook called external regressors. Let's click on that. So these are the notebook that walks you through how you can integrate these external regressors, so multivariate time series, exogenous regressors, and make forecasts based on it. So just give me a few seconds. Yeah. So this is also what I was talking about a few minutes ago. Local univariate. Okay, so if you scroll down a little bit, you're going to see that it has a different input format or structure, because now we're using also additional columns to make a hint for forecast. Yeah. So similarly, we have also global external regressor notebooks and also foundation model notebooks as well.
Amazing. Okay, good. So then everything is supported, and then some models are supported, some not, depending which model you choose.
Yes. Yes.
Okay. Amazing. And then, Ryuta, can you show us the configuration before you kick off the job for this training?
Yeah.
And
okay,
can we
so yeah, go ahead, Maria. Sorry.
No, can we go through the different configuration options there? And let's discuss a little bit what do these configurations mean, and like how should we tweak them depending what we want to do?
Yeah, absolutely. So here, so this is the most important function that comes from MMF, run forecast. Oh, let me zoom in. And so these are all the input parameters to specify the configuration for your forecasting solution. So for example, you point to the delta table where you have your training data set stored. And these two tables, scoring output and evaluation output, that we're going to take a peek at it a little bit later. But this is where we're basically writing our evaluation result, our forecasting result into. These are also delta tables. And here we specify which column stores the grouping ID, which column stores the date, what is our target variable, what's the frequency of our time series, what's our prediction length, so how many steps ahead we want to forecast. And these are really important configurations where it allows you to specify your backtesting strategy. So this is a monthly forecast. So in backtest month means how many months in the history you want to go and start your backtesting trials. So we're saying that 12 months. And the stride is, like the window that you move every time you go to the next backtesting strategy.
And then the frequency it can be anything, like day, month. Do we support specific things, or it can be?
Yeah, currently we support daily and monthly.
Okay.
But we have another engineer working on hourly forecast. And then, so yeah, and it's an open source with a lot of comments in the source code. So you can also easily upgrade the code base to integrate weekly, hourly. We're just collecting enough evidence right now from the field, which resolution it makes to add.
Okay, amazing. And then with these configurations, then we can prep all our training jobs so that then it does the validation automatically for us given the configurations we do here. So mainly we configure this and then it goes, kicks off the job, does all the back testing, and then we just review everything in MLflow.
Yes. So not on MLflow, we're going to be reviewing everything on a Delta table.
Oh,
I'm going to show you what that means. So these are the two tables that it produces. It generates. When you run a run forecast functions, it generates two Delta tables. One is called scoring output, and the other one is called evaluation output. And now I just want to quickly show you what these tables look like. So we're looking at the scoring output table. And this table stores forecasting result from all the models that you applied to all the time series that you had on your training data set. And here I'm just filtering on N1. So I'm just showing you N1. You can see that I applied 38 different models, and we're getting a forecast from each model. So remember we said we want to produce 3 steps ahead forecast. So these are the forecast that's coming from different models. But you don't know which model performs the best given this time series. And that's why we have this evaluation output table here. So again, we're filtering on N1. And what this table stores is the results from all backtesting trials from all models for all time series. And what it means is the following. So given this model, Chronos T5 base, we have 10 different entries. This is because we said we wanted to use last 10 months for backtesting. And for each one of these entries, we have different backtesting window start date. And at this point, we are producing a forecast 3 steps ahead into the future, but it's still a history. And we expand this. So we have 3 steps ahead forecast, as if forecast, but this time we actually have actuals because this is a backtesting. And you can basically look at the residuals between the actuals and forecast and construct your own metric, or you can use out-of-the-box metrics that we provide. And what you want to do afterwards is you would want to aggregate these metrics across all these 10 different trials and assign a single value to this model, Chronos T5 base. You do that exercise for all different models. So for each model, it's assigned to the aggregated metric. And now you can say which model performed the best given this time series.
So just to make sure that I understand right, you're telling me that because you write everything to those delta tables, you have the flexibility to either evaluate that automatically with your chosen metric, or if people want, they can also use those residuals to just build whatever metric they prefer.
Yeah, you're right. And that's a lot of requests that we also heard from the field. Customers actually don't want to use out-of-the-box metrics most of the cases, because if you think about demand forecasting, overestimation carries a different cost than underestimating. And it's very business-specific cost because over-ordering, you pay the price for the storage until it is sold. And underestimation means that you directly lost that demand. So they wanted to assign asymmetric, a different cost to those residuals. That's why we decided to expose both the as-if forecast and also the actuals.
Super useful.
Amazing, yes. And then do we aggregate these somehow for them through the package, or they have to do it themselves?
Yeah, right now they have to do by themselves, but it's an easy SQL query where, so this is a simple query that takes the lowest aggregated SNAPE given a time series and given a model, and then it just selects the forecast. Remember that forecast table that shows the forecast result? it calls that forecast from that table. So we can see that, so here we have 1,000 different time series. And for each one of these time series, we have the best performing model, different best performing models, first of all. And you have the aggregated SNAPE. And then we are taking the forecast from each one of those models.
Beautiful. And then they can push it into a dashboard and monitor across
Yes, they can. Yeah. You can also decide to choose multiple forecasts and do aggregation or reconciliation based on that evaluation table.
Very nice. And then can we discuss a little bit how is the hyperparameter tuning happening? Because probably these models have different tuning parameters we need to configure. So how is this taken care of behind the scenes?
Yeah, so for hyperparameter, we perform that under the hood. This is automated, but you can provide the search space through a configuration file. And if you go to one of the notebooks, let's say we look into global models, and you want to, so these are neural network-based models, and they come with a lot of hyperparameters you can tune. For example, number of layers, learning rate, and so on. So for these, you can tune them here. So some of these models perform hyperparameter optimization, and you can tune them directly onto in this configuration file that is linked here, which will take you to, which is basically this file, models_conf. And this stores also all the active models that is available right now. If you scroll down to deep learning based models, so for example, for NBEAT, you can specify these hyperparameters or range of hyperparameters you want to perform search. So this is the location where you set that range.
Okay, so by default we have some pre-configured space, or whoever runs this can go and update it.
Yeah, by default it is this.
Okay,
but if you want to customize it, you can also customize directly into this configuration file.
Excellent. My last question is, what happens actually behind the scenes when you kick off this job? So how does this scaling works, and how much can we push the scaling? So do we need to track specific metrics? So how does this work?
Yeah, so it does work differently for different classes of model. So for local models, we use something called pandas UDF, which basically subsets your data set into, let's say, time series. And then it does the fit and the predict in each executor worker in parallel, so that you can, you can fit and predict at the same time across multiple time series. That we use for local models. And for deep learning based models, we use a technique called DDP. So you replicate the models into multiple GPUs, and then you perform forward propagation, backward propagation synchronously, and update the weight accordingly.
Very nice. Sorry.
And for time series foundation models, you can fine tune, but you don't need to fine tune. It depends on what you want to do. So training is not done. We just use the model as is.
Is there, for the first case, for the pandas UDF case, is there then, depending how many runs you want to do, like, is there any rule of thumb or how to create the cluster that you need to have available? Like how big the cluster should be, or?
Yeah, so it is embarrassingly parallelizable because the fitting and the prediction of these local models is independent from all the other fitting. So it really depends on your business requirement. If you have a tight time window that you need to generate a daily forecast within 1 hour every morning, then you basically horizontally scale your compute in order to fit that requirement. But then you also have to be careful about the cost and so on. But so for the first case, it is just based on the requirement. I've seen customers scaling all the way up to 1 million. 1 million time series. They were using lots of workers.
So like 1 million cores, let's say, probably one is running in each core of the cluster.
Yeah, or like they were not parallelizing at the same time, so they
Okay.
would still like do, yeah, not 1 million cores, but maybe a few thousand cores.
Okay.
Yeah.
Amazing.
And process 1 million incrementally.
Okay, so then depending the time you have to create the forecast, you can scale your cluster much more. So throw more compute to create your forecasts in less time, but obviously more expensive.
Yeah, that's the case. You said 1 million core is an extreme case when you want to
Yes.
get everything done instantaneously. Yeah, you can do that as well. Yeah.
Okay, sounds good. Any other questions? Anything new that we missed?
Maybe just a little bit about this new type of model called time series foundation models. So I said these are new type of models, and a lot of renowned institutions, companies are working on it. They're making most of these models public, and if you look at their papers, you see that the model creators model always perform the best in their benchmarking exercise. But this is because the validation dataset is not unified. So there is no a single validation dataset that allows you to benchmark all your new forecasting models. When we saw these papers having inconsistent, let's say, result, we came to this conclusion that the performance of the model really depends on individual time series. So there must be a way for you to select the best performing models for each time series and not on a set of time series. So this is the reason why we came up with this idea of fine-grained model evaluation and selection, which MMF allows you to do.
So you say that one time series may be better fitted for a specific model and another one, which can be part of the same, as in one SKU of a product can be very nicely predicted with a very simple model, whereas the other one probably is something more complicated and could need a more, clever foundational model.
Yes. And it can also depends on the time when you do a forecast. Sometimes it can change. Yesterday, Arima was the best model for time series A. Maybe tomorrow it's not anymore.
Okay.
Because the underlying data generation process changed. So I think it's an active field of research. Which paradigm and model is best for what kind of time series?
Amazing. Cool. Thank you, Ryuta.
Oh yeah, last, I just want to show you something very interesting. Yeah. So for these time series forecasting models, you don't need to train anymore because they come pre-trained. In MMF, if you use these models, they will be automatically logged and registered into your catalog.
So they are logged like from Hugging Face or something. They are downloaded from from whatever and kind of logged into registry.
Yes, that's right. So let's see.
The second time you want to use it, does it know it has already registered it?
No, it doesn't. It's going to download this model again, and then it's going to log and register this model once again. But you get to keep the snapshot of that model. It doesn't update that often, but it might. So for that case, it guarantees you the reproducibility. So here, you have all these models being logged. And let me just show you one. Kernels tiny M4 daily. It is being logged and registered into Unity catalog. What now you can do, you can serve this model into model serving. Because you don't have to think about training anymore. You can serve this model behind an endpoint, and you can always send request. So,
amazing.
And then it's going to come back to you automatically. So this has been a very challenging task for time series analysis, especially around monitoring and tracking. So when you want, anomaly detection on the fly, and we think time series foundation models can open up a lot of application in this field, because when your recording observation is significantly different from what the model predicted, you can immediately flag it as an anomalous data point.
Okay, I have two questions here, sorry. So for the first thing that we said, that it goes and downloads the model automatically, does it download a specific version of the model so that we ensure reproducibility? This is what we are saying, right? So it's just going to go on a specific model version, download this one, and make sure we are using the same model version that we had in the config.
Mm-hmm.
Yes?
Yes.
Yeah. Okay, cool. And the serving part, it's not necessary for running a job on the many model forecasting. It's just an extra thing that then you can serve it and use it in other applications or for testing and drift.
Yes, you're right. This is like an added value, new way of using forecasting model on the fly.
Okay, and this is usually used by whom, like analysts, for example, or other applications or other business stakeholders?
Yeah, so for example, if you have a Power BI dashboard,
yes.
You have a historical time series being visualized on the dashboard.
Mm-hmm.
And if you click on this timeline, it can also produce a forecast for you. Under the hood, it can also it calls this function or model being stored behind the model storing point, and it gets the prediction back, and then it visualizes on the dashboard. That's one use case. Yeah.
Very nice. Excellent.